There's been a pretty considerable snowstorm today. I'm definitely not going to be leaving the house, so now is as good a time as any to start work on the Coilgun. So I am in my notes web app thing that I made, and what you're seeing here is all of the individual things I need to accomplish to finish the Coilgun. And the first thing on here is the capacitor charger. So that's what I'll try and tackle today. So as you can see by what is written here, my intent is to make a DC to DC boost converter with a variable input and variable output voltage. So this is a standard schematic for a boost converter circuit. Generally a very simple circuit, and there's really only 4 components here. Over here is your power source, then you have an inductor up here, a diode here, some sort of capacitor on the end here, and then a switch of some sort here. This is supposed to represent some sort of transistor, specifically a MOSFET. It is hastily drawn, but bear with me. As a capacitor charger, this is what it would look like, but if you're just using it to step up the voltage, you would have a load that would be across 2 points here and here. You drive it with a high frequency square wave at the base of this transistor here, so it's turning on and off very quickly. When the transistor or switch or whatever is closed, current flows around in this loop. So when this is the case, the only load is the inductor, and the inductor is creating an electromagnetic field around it. Now when the transistor turns off, the current follows a different path. Instead it goes around here. And while this is happening, the electromagnetic field stored in the conductor collapses because it's no longer being shorted through this transistor. So that energy then creates another series voltage across the inductor. What that means is that you then have the source voltage from the power source here in series with the voltage across the inductor. You add them together, and then that voltage goes into your capacitor, which is stored over here. So this way you are increasing the voltage. And it's not just a small increase or anything like that. It can be a very significant increase in voltage across it. There's also this diode here, which serves a simple purpose, but is absolutely necessary. When this transistor turns on and shorting the power source across it, this capacitor would be likely to discharge through this transistor. Instead, this diode inhibits that, and the capacitor cannot discharge through it, and it maintains the voltage. So I've been working on this for a little while, trying to optimize everything, and this is what I've come up with. It's all pretty messy right now, but it's just a prototype, so it's kind of expected. So here I have 3 large current inductors, and then over here there's a couple of n-channel MOSFETs, that's my switch, and then over here there's the diode. And then back here is the capacitor I'm using. This is one of the ones that I plan on using on the final product. It is 1500 microfarads and has a peak voltage of 250. So my goal with this is to step up a voltage of around 12 to 24. I'm not sure which one yet, but up to 250 volts to get the full energy storage out of these capacitors. And over here I have an Arduino. The only purpose for this in this circuit is to create that high frequency square wave. So this does work, although not as well as I need it to. So I'm going to turn it on for just a little bit. The power supply is set to 8 volts right now, and you'll be able to see it work. So I'll turn it on just a little bit. It's drawing about 1.5 amps. I'll turn it off. Now if I carefully measure the voltage across these 2 capacitor leads, it's about 86 volts. So 86, that's pretty good. I'm going from 8 to 86, so it's more than a 10 times increase, but it's still not 250. So it's still not quite where I want it. Then I'll discharge this to reset it. Now if I was using a 24 volt battery, 24 volt power supply, a 10 times increase would be enough to get me up to that 250, or not necessarily exactly 250, but it'd still be good enough. Unfortunately though, this increase is not linear. It's not proportional to the input voltage. So if I unplug this, turn this on, I'll set the voltage up to 12 volts. Now if the output voltage was directly proportional to the input voltage, you would see a 50% increase in the output voltage here. So somewhere around 120 volts. If I turn it on for a little bit, it's drawing a lot more current, and then measure the voltage across here, we still get 86 volts. If I were to left it on longer, it might have been able to get up to 90. The most I've ever gotten with all ideal parameters is a little over 100, like 102, 103-ish volts. But that's not going to be anywhere near enough, so I'm going to need to significantly change this. Unfortunately, I don't think I'm going to be able to get the required voltage out of a boost converter. I'm going to need to significantly change things up here. But at least I can make some cool sparks. Fortunately, there are other ways to generate somewhat high voltage without using a boost converter, so I do have a backup plan. These are the inductors I've been using. They're pretty beefy. These are toroidal inductors, which means that their core is a toroid. A toroid is just that donut shape on the inside there. And that shape in particular is really good for something like an inductor because it creates a closed loop magnetic circuit. And it means that the field is longer lived and potentially stronger. What it also means is that these toroids act kind of like a transformer, just a transformer that's missing a second coil. Because a transformer is also just a closed loop magnetic circuit just like this. And since these are so large, I think I could make a transformer out of these. So I've counted it all up and there are 27 windings total, which is not a lot. And using that many windings on a secondary is nowhere near ideal. But as you can see, there are 4 wires here, not just 2. The intent is that you wire both sides together so it effectively is one thick wire, but you don't have to do that. What I can do instead is wire 2 of these wires on opposite sides together diagonally. So then what I essentially have is, instead of 27 thick high current windings, I would then have 54 windings that are just rated for half the current. And 54 is much better for a secondary winding. Again, still not ideal, but significantly better. So then what I can do is I can get 5 windings around here with some thicker gauge wire like this, and then use that as a primary, and then going from 5 to 54, that's a little over a 10 times increase in the voltage. And then I would just have to drive it like a flyback, just running an oscillating current through the primary and then getting an oscillating current out the secondary. And then to charge the capacitor, I simply have to make sure that we're under 250 volts and then rectify the current to make a stable DC. And using a transformer like this for high voltage is a much more tried and true method than a boost converter. So if anything should work, it should be this new idea. It might be a little bit difficult to get 5 high gauge wire windings through that center hole there, but I do think it's going to be manageable. This is the wire I've got. It's 16 gauge with rubber insulation. It's pretty thick, but I think it should work. I was just able to get all 5 windings around there, and I got them in pretty much as tight as I can. And the friction in there also holds the wire in very nicely, so that's convenient. And it looks pretty mad sciencey too, so that's always a plus. Now we need to do the part that could prove to be quite challenging, and that is making the full H-bridge, which I'll use to convert DC to a square wave AC to power this transformer. It is now the next day, and the circuit has become considerably more complicated. So I've got my makeshift transformer on the end here, and then I've got 4 MOSFETs, each with the corresponding drive circuitry. 2 of them are N-channel, and 2 of them are P-channel. So if you know anything about electronics, this might look familiar. What I'm doing here is I'm creating an H-bridge, and I'm using that H-bridge to create a modified square wave AC signal to go into the transformer. The idea behind an H-bridge is quite simple. This is the general schematic. Imagine that these circles represent MOSFETs. I didn't want to have to draw them all out. So with this configuration, if I turn on this MOSFET and this MOSFET, the current will run over here, down through it, and across the load in this way, coming back to ground through the other MOSFET. Then if I instead turn on the other pair of MOSFETs, this one and this one, it'll go through the first one across the load in the opposite direction, down through the other MOSFET to ground. So then if I oscillate going back and forth between this pair of MOSFETs and this pair of MOSFETs, I will create an AC voltage across my load, which in my case is the primary coil of my transformer. I can also add a slight delay between that transition to create a modified square wave. So a normal square wave looks something like this. A modified square wave is a better approximation of a sine wave, and it looks something more like this. So I've got my H-bridge MOSFET configuration, which is feeding into the primary coil of the transformer. And then on the secondary here, I just have a little diode in series to rectify the AC, which is then leading into one of my capacitors. So this transformer has a theoretical voltage increase of 10.8 to 1. So I'm looking to get a approximately 10 times increase from the input voltage. So the capacitor is discharged right now. If I go ahead and turn on the power supply at 8 volts, You can hear it hum a little bit. I'll turn it off. Now if I read the voltage across the capacitor, I get 12.7 volts. So when I originally did this, I was fairly disappointed. So my input voltage is 8 volts, my output is 12, that's only a 50% increase, that's nowhere near the 10 times increase that I'm looking for. But what I've done here has actually exceeded my expectations, and it's all actually working very well. And it took me quite a while to figure out why it is that this is actually a success. So after much experimentation, I finally figured out that the voltage across the primary is not 8 volts as you would expect. Though the input voltage is 8 volts, the actual voltage across it is only about 0.7 volts. So right here I have a couple of jumper wires, just like all the other wires that I've used on this breadboard circuit. Now if I measure the resistance across one of them, I get a very nominal resistance of around 0.2. And in reality, most of that resistance is probably just coming from the leads themselves, so it's probably more like 0.1 ohms or just milliohms. And the other one is the same. Here I have another breadboard. If I go ahead and just plug these jumper wires into the same line on the breadboard, and now if I measure the resistance across them, depending on how I hold it, I can get up to over an ohm. So right now it's at 0.7, it fluctuates between over an ohm to around 0.6 ohms. So the wires themselves have very little resistance, but the connection points have very high resistance relative to the rest of the circuit. The other important thing to note here is that the primary coil, it has very thick wire and it's very short length of wire. Both of those mean that it has a very low resistance. I've measured the primary resistance to be around 0.2 or 0.3, and now every single one of these breadboard connections can have up to an ohm of resistance. And there are multiple connections before and after the primary coil in series. So we have a very large resistance in front of the coil, then the coil itself, and then a very large resistance after the coil. So what this does is it creates an extremely high voltage drop before and after the actual load itself, which results in only having a true input voltage of around 0.65. So in reality, having an output voltage ranging from around 10 to 15 is very respectable because the input voltage is only a low 650 millivolts. Being that the input voltage is so low, I would only expect around 7 volts on the output, and in practice, I get much more than that. You can also see that if I leave it on longer, over time, the voltage increases. It immediately starts out at around 7 volts, but then it continues to increase, so now it's over 15 volts. To be frank, I don't really know why this is happening. This capacitor is acting as a kind of boost converter, and the voltage continues to increase even after it has reached its theoretical maximum. But I'm not complaining. If anything, this is a good thing. So in practice, this circuit is capable of multiplying the voltage by over a factor of 10, even up to a factor of 20, even approaching 30, which is significantly more than I need for this project. But of course, we do still have a true input voltage of 8 and an output voltage of around 15, which won't cut it. So what I need to do is I need a custom circuit board. These high resistances come from friction-based joints. And if I had a custom circuit board, there would be none of that. It would be as close to an ideal circuit as possible where there's no resistance through the wires. With a custom circuit board, you would have very low resistance before and after the load, so then you would, of course, have a very low voltage drop, and you wouldn't have this kind of problem. So now I need to design that custom circuit board and get it sent to a manufacturer. This is not at all ideal because I don't know for sure that this circuit will work once you get to higher voltages and that a custom circuit board would solve all my problems. I'm pretty confident it would, but I don't know for sure. And I'd rather not waste time and money on custom circuit boards when I don't know if that is the solution. But unfortunately, that really is my only option at this point. So I wasn't quite able to get up to the full 250 volts today like I had hoped, but I do think I have developed a circuit that will be capable of doing so once I have the right materials. So I'm very happy with my successes today, and I'm very excited to keep moving on with this project. There's certainly going to be much more to come, and it only gets more interesting from here, so stick around, but this is all I have for now, so bye.